Okay, so our next speaker is Artem Chernikov, who will speak about idempotent Keisler measures. Please.
All right, thank you very much for inviting me to give a talk here. And I apologize for not being able to attend some of the other talks because of the time difference. But all right, yeah, so today I will talk about idempotent Keisler measures and convolutions. So this is a topic on the intersection. Well, it's mostly in model theory, but it has connections to topological dynamics, and to ergodic theory a little bit, I guess. So this is joint work with Kyle Gannon, who is a postdoc at UCLA currently. So let me begin with some background to make sure we're all on the same page. So this is some more or less standard model theoretic notation. I just want to quickly overview it. So throughout the talk, T will usually be a complete first order theory in some fixed language L. I will denote by this bold M a monster model of T, which usually means kappa saturated, kappa homogeneous structure for a sufficiently large cardinal kappa. And curly M will usually be a small elementary submodel. Okay. Now, as usual, given a set A of parameters, and when X is a tuple of variables, so I'm not going to write bars over my tuples of variables. It can be a tuple, can be a singleton, doesn't matter. So we denote by S subscript X of A the set of complete types over A. Okay. So similarly, we'll denote by Lx of A the set of all formulas in the variables X with parameters in this set of parameters capital A. Up to logical equivalence, okay? And we identify it with the Boolean algebra of all A definable subsets of the corresponding sort of the monster model, but only using parameters from A. And I will simply write Lx when I'm not allowed to use any parameters, yeah? So this is just for the formulas without parameters. So of course, types in this space of types, complete types, are exactly the ultrafilters on this Boolean algebra of definable sets. And by Stone duality, we know that the space of types over a given set of parameters is a totally disconnected compact Hausdorff topological space. And the standard basis of Clopin sets for this topology is given by sets of this form. So for a formula, I just consider, for a fixed formula, I look at all types which it belongs to. Okay. And I will also refer to types over the whole monster model as global types. All right, so this is just some standard terminology. Now let me talk about the main topic of my presentation today, Keisler measures. So a Keisler measure is simply, okay, so you should think about it as a generalization of types, for example. So a Keisler measure mu in a given tuple of variables X over a given set of parameters capital A is simply a finitely additive probability measure. So it means it takes values in the interval 0, 1 on the Boolean algebra of all A definable subsets of the corresponding sort of the monster model Mx. Okay. So, and by this fracture Mxa, we will denote the set of all Keisler measures in a given tuple of variables over a given set of parameters. Then this set of all Keisler measures or given set of parameters is a compact Hausdorff space with a topology induced from the product topology. So namely, each measure is a function from formulas into 0, 1. And so we can view it as a subset. And moreover, the conditions expressing that it is a measure define a closed subset of the product space. So this becomes a compact Hausdorff space, but of course, no longer totally disconnected. Now, a standard basis for the space is given by the open sets of this form. So if I fix some n, I fix some finite n many different formulas, and I fix the corresponding real numbers, then I have I'm allowed to have finitely many conditions of the form. The measure of a given formula or a given set in the Boolean algebra of definable sets is between these two values. Okay, so I consider all measures of this form, and these are the basic open sets for this topology. We can also view types as Keisler measures. So I can identify a type with the measure which Dirac measure just concentrates on this one point, the type. While this identification, we think about the set of types as a closed subset of the space of measures. Okay, and moreover, the space of measures is equipped with a topological vector space structure. Sorry, not the space of measures itself. Space of measures is a convex, closed convex subset of a topological space of all real valued, topological vector space, excuse me, of all real valued measures, not necessarily probability measures. Okay, and just remark that this topology, the way we define it here using this logic formalism, is the same as the usual weak star topology on the space of measures. The reason for this is that every Keisler measure can be extended uniquely to a regular and this time countably additive probability measure on the Borel subsets of the space of types. This is just using Karateadore's theorem, for example. And then the topology we defined above corresponds to the weak star topology. So a net of measures mu I converges to a given measure mu if the corresponding integrals converge for every fixed continuous function phi f from the space of types to the reals. Okay, so that's it for the space of Keisler measures. And feel free to interrupt at any moment if you have any questions about what I'm saying. So we have the space of measures, which we view as a generalization of the space of types. Now, let me give you a couple of examples of Keisler measures. So, of course, we can take averages of types. Okay, so for example, in any theory, if I'm given countably many types, pi, over some given set of parameters, and I fix some real numbers, ri, so that the sum is 1. Yeah, so the sum converges to 1. Then we can define mu to be the weighted average of this sequence of types. So we take a type pi with the weight ri. Okay, and since the sum of the weights is 1, this indeed defines a probability measure, a Keisler measure. So I might omit the word Keisler in this talk. I might just say measure instead of Keisler measure from now on. Okay. All right. So we have this this example. Let's consider a couple of other examples. So let's consider the simplest possible structure, the theory of an infinite set, yeah, with no additional structure, and assume that X is a singleton. Then the space of types, of course, is given by the realized types. So the space of global types is given by the realized types and one non-realized type, excuse me, which I denote as P infinity. So this is just a type which says I'm not equal to A for every A in the monster model. Now the theory obviously has quantified elimination, so we can see that every formula is just a Boolean combination of equalities of formulas of the form X is equal to A, and from this it's easy to see that every Keisler measure in this theory, in this structure, is in fact of the same form as in 1. So it's just a weighted sum of types. Okay, and this holds more generally. So the same is true for in an arbitrary omega stable theory. So this includes not only the theory of an infinite set, but it includes any, for example, any strongly minimal theory. So let's say algebraically, the theory of algebraically closed fields. of any given characteristic. Okay. So in this case, again, every measure is just a sum of types. So this requires a little argument due to Keisler arguing with the Morley rank, since the Morley rank is bounded in omega stable theories. Okay, so all measures in such theories are of this extremely simple form, but in general, of course, they can be more complicated. So already in the example of a dense linear order, so just let's say reals with the ordering, we can take lambda to be the Lebesgue measure on R, and then we can use it to define a Keisler measure. So namely, given any formula, phi of x, I can define the measure of this formula, so mu of phi, to be the Lebesgue measure of the set of solutions of this formula phi intersected with the interval 0, 1. Okay. Of course, in DLO, the set, because in DLO we have quantified elimination, this is going to be a Borel set. And so it makes sense to talk about its measure. And with this definition, we clearly have that mu is a Keisler measure. So it shouldn't say mu of x, it should be just mu, excuse me. Then mu is a Keisler measure. But it's also not hard to check that it is not a sum of types. So it's uniformly spread on the interval. Okay, so these are some examples. So now I want to talk about some operations on measures. Well, first on types and then on measures. So ways to build new measures from given ones. So namely, we have a certain notion of an independent product. So you can think about this independent product as a way to canonically choose. So if I'm given two types, okay, let me start with types first, and then I'll comment about measures. So first of all, we have an independent product of types, okay? So assume I'm given two types, P in the variable X and Q in the variable Y, and assume that P is invariant under all automorphisms of the monster model that fix some small model curly M pointwise. Yeah. In this case, we can define a type which we denote as P tensor Q, and note that this is a type in the variables X, Y. Okay, so it's now a type in two variables, or more precisely in the concatenation of the tuples of variables X and Y, which we define as follows. So for any small n, an elementary substructure of the monster model, I'm going to let P tensor Q restricted to this small model n. So it means I only consider formulas with parameters from n. So we are going to take this to be the type of AB over this small model n for some B realizing Q over n, and some A realizing P over n, and this B as well. Okay. Now, why this? Why do I say here some any? So this is the point of starting with an automorphism invariant type M. So since P is automorphism invariant, it follows that the formula belongs. Okay, so let me just spell it out. So here, automorphism invariant means that for any phi of x b, we have and b prime such that b prime has the same type as b over the small model M, we have that phi of xb belongs to P, if and only if phi of xb prime belongs to P. Okay, so it's another way to formulate automorphism invariance, because we are working in a homogeneous structure, so having the same type is the same as being in the same orbit under automorphism fixing M. And so then it means that it doesn't, the choice of a representative of a realization of Q doesn't matter here in this definition. Yeah. So this is what makes it well defined. So this way we have defined this independent product of types. Let's consider a couple of examples. So for example, if P is a non-realized type in the theory of equality, we can consider the product of P with itself. Yeah, so I can consider the tensor product of P of X, tensor P of Y, yeah? Where P is the same type, the non-realized type. Then this type is axiomatized by, first of all, saying that X is not equal to any A in the monster model. Similarly, Y is not equal to any A in the monster model. And also, X is not equal to Y, right? Because any realization of the tensor product is that by definition is the type of AB, where first we have B realizes P, and then we have A realizes P over B. So it has to say that X is not equal to B, right? And that's how we get this part. Okay, so this defines a canonical way to extend the product of two types to a complete type and two variables. Another example, excuse me, another example, we can consider the type at plus infinity, excuse me, in the theory of DLO, okay? So again, we know it's a complete type, just saying I'm greater than A for every A in the monster model. So in this case, we can consider the type P of X tensor Q of Y, which is going to specify that X is greater than A and Y is greater than A for all A in the monster model.
Sorry, Q should be the same thing as P. Q is the same as P.
Oh, yes. Yes. Thank you very much. Sorry, yes. Here, in both cases, Q should be P. Yeah, thank you. So we have that P of X tensor P of Y is given by this type, which says X is greater than Y. But importantly, if we consider the product in the opposite direction, so we take P of Y tensor P of X, then this is a type which is going to say in particular that Y is less than X. Okay, and so this shows that the order of this product actually matters. So it's not hard to check from the definition that this operation tensor product is associative on invariant types, but not commutative, as this example demonstrates. And in fact, stability of a theory is characterized by this operation being commutative on all types, all invariant types. All right, so this is the product operation on types. Now, using this, we can specialize to the situation when the theory T expands a group. So, as usual, this simply means that for any model M of T, we have an operation which is definable and is a group, satisfies the axioms of a group. So in this case, given here I should say invariant, given two invariant, when I don't specify the small model over which they are invariant, just assume there is some small model over which the two types are invariant. So in this case, given two invariant types, we have an invariant type which we denote as P star Q. Yes. And we define it by combining the independent product of types and the group product in the sense of the underlying group. So we define it via saying that a formula belongs to the product, and note that this product is in the same variable as the types P and Q. Okay, so we define it by saying that phi of X is in this convolution product of two types if the formula of the form phi of X times Y belongs to the independent product. And this is a formula in two variables now, of course. Okay, so this is a way to define it. Equivalently, we can say that P star Q is simply the type of A times B over the monster model for some any pair AB realizing the tensor product of P and Q in some larger monster model. Yeah. So we can also realize it in some larger model. So this is the idea. We take the group product of two elements which realize an independent product of the types. Okay, and so now a bit of notation. So given some small model M, we denote by as inf the set of all global types which are invariant with respect to the automorphism group of the monster fixing this small model M. And we define the set of finitely satisfiable types. So S of Fs is going to be the set of all global types finitely satisfiable in M. Where by finitely satisfiable, we mean as usual that phi of x belongs to P implies phi of x has a realization in the small model M. So phi of A holds for some A in the small model curly M for every formula in the type. So this is a strong form of invariance of a type. Okay, and then both of these groups, so I write dagger here to mean Fs or inf. So both of these semigroups are, well, first of all, both of them are semigroups with respect to this operation, and moreover, they're compact and left continuous. Where by left continuous, we mean that the map from this space to itself, where we fix some type Q, okay, and we vary the type on the left. So multiplication by a fixed type on the right defines a continuous function from the space to itself for every fixed type Q. It is not right continuous, however, and certainly not jointly continuous in general. Okay, but in the case, for example, of a stable abelian group, this is continuous on both sides. All right, so we have defined this notion of a convolution product. You might be familiar with this convolution product. Well, it plays an important role in model theory, but outside of model theory, it is often used in the discussion of idempotent ultrafilters. So let me just make a remark connecting the two directions. So a type, either finitely satisfiable or invariant type, is said to be idempotent if P times P is equal to P. Yeah. So for example, okay, to give you an example, we can consider the structure M to be Z plus, and we add a lot of new predicates, P and alpha, where P and alpha lists all subsets of Zm. So for all n, so we name all subsets of this model of powers of this model by new predicates. Okay, so then all types over the structure are definable because simply we named everything. And idempotent types, in the sense of the definition we just discussed, are going to correspond precisely to idempotent ultrafilters in the sense of Gelvin-Glazer's proof of Heinemann's theorem, for example. So it's a popular technique in so-called, I guess, partition combinatorics on the integers, on the natural numbers, which is used to prove a lot of various combinatorial theorems, for example, the celebrated Heinemann theorem. So my point here is that the setting of idempotent types, it extends the setting of idempotent ultrafilters. Yeah, because now we are not necessarily considering the Boolean algebra of all subsets, but we're only considering the Boolean algebra of subsets in a given structure, definable subsets in a given structure. But of course, we can always name all subsets, and then we are in the familiar setting of idempotent ultrafilters. Okay, now in stable theories, idempotent types are known to arise from type-definable groups. And I'll comment later on this in more detail, but this is parallel. This is actually remarkably parallel to a certain classical line of research in topological group theory. So I would like to briefly mention this. So forget model theory for a second. So now we are in the context of locally compact groups, locally compact topological groups. Then the space of regular Borel probability measures on such a group is equipped with the convolution product, which is defined, so the product of two measures, mu and nu, is the measure of mu times nu of a set A, a Borel set A, subset of the group, is given by integrating the characteristic function of the set on the product x times y first with respect to x and then with respect to y. So it's defined by this double integral. It's an important operation in Fourier analysis, etc. So if the group G is compact, then there is a very nice classical characterization of idempotent measures in this setting. So it's known that mu is idempotent. So again, meaning that the product of mu with itself is just mu. If and only if the support of mu is a compact subgroup of G, and moreover, mu restricted to the support is the higher measure on this compact subgroup of G. So this is a classical theorem first proved by Kawada and Ito in the 1940, and later discovered by Wendell in 54. And this started a whole line of research. So the same characterization, for example, extends to locally compact, but now abelian groups. This is work of Rudin and Cohen. So this is Paul Cohen before forcing. So this was some very nice theorems. And later this theory was pushed further into compact topological semigroups or semi-topological semigroups, etc. But there the picture rapidly becomes increasingly more complicated. Okay. Now, what in our joint work with Kyle, what we wanted to understand is the common some unification of these two pictures. So we have this this results about idempotent types in model theory, and we have this classical picture of measures in compact groups. And we want to understand this by combine these two lines by understanding actually idempotent measures, idempotent Keisler measures in definable groups on the model theory side. Okay, so now what do I mean by convolution of Keisler measures? So let's define this. This is going to be a generalization of the free product of types that we just discussed earlier. So first of all, we have to make sense of the convolution product of Keisler measures. Okay, so here we need a slightly stronger assumption on the Keisler measure. So assume we have mu, a global Keisler measure. We will say that such a measure is Borel definable over some small submodel M if we have the following two conditions. So first of all, it is automorphism invariant. So it's invariant under all automorphisms, fixing the small model M pointwise. So here I phrase it like this. For any phi of xy and parameter b, the measure of phi of xb depends only on the type of b and not on the particular realization of its type. Okay. In which case, we can write simply mu of phi of xq, where q is a type, to denote mu of phi of xb for some b realizing q. Okay, so hence we can think about the measure in such, if the measure satisfies this condition, we can think about it as a map from the space of types over the small model M to the interval 0, 1. Okay, and then we say that mu is Borel definable if this map is Borel. And the measure is said to be simply definable if this map is continuous. And this notion of definability coincides, for example, with the usual definability for types in the case when our measure is a type, is a 0, 1 measure. Okay, so now given this notion of Borel definable measures, we can define a product for them, a free product of measures. So given mu and nu, where mu is in the variable x, nu is in the variable y, and now we assume that mu is Borel definable, then we can define the free product, mu tensor nu. It's a measure in two variables now, x, y, by saying that the measure of the formula phi of xy is going to be the integral over all types in the variable y, where we simply take the value of mu phi of xq. So q varies over the space of types, and we integrate with respect to the measure nu on the space of types. So note by what I remarked earlier, every Keisler measure can be extended to a regular Borel probability measure uniquely. So there is this unique correspondence. So then viewing mu as a measure on the space of types over the small model, this integral is now well defined because mu is Borel definable. So this is a Borel function of Q. Okay, so this integral makes sense and defines a free product. So a couple of remarks about it. Oh, yeah, and I actually would like to restrict to the case of an IP series for simplicity. The point here is that I define it for Borel definable measures. In general, there is no good definition for simply invariant measures without the requirement of Borel definability. It's not obvious how to make sense of some integral like this, unlike in the case of types, where we only needed invariance. So here we need slightly stronger condition, Borel definability. But in the case of an IP series, there is no difference because in an IP, every automorphism invariant measure over a small model M is in fact Borel definable already. So then the free tensor product operation, the free product makes sense on all invariant measures. And this operation extends the tensor product on types, on invariant types that we discussed earlier. Okay, so now by analogy, if our theory expands a group, we can define the convolution product of two Keisler measures, of two invariant Keisler measures. So namely, we define mu star nu via saying that the measure mu star nu of a formula phi of x is the measure given by the tensor product mu x tensor nu y of phi of x times y. And if you unwind this definition, you see that actually it also corresponds to a double integral, like in the classical definition of the convolution operation. Yeah. So this is indeed is an analog, definable analog of the convolution operation in the classical situation. As I already remarked, if we restrict to types, so if both of our measures mu and nu are just invariant types, we get the same convolution product we had earlier on types. Okay. By analogy with types, we define, we let M inf to be the set of global automorphism, global measures invariant with respect to automorphisms of the monster model over the small model M. And similarly, we define the set of all global finitely satisfiable measures in M. So for a measure, by finitely satisfiable, we mean that if mu of phi of x is greater than 0, then there exists some A in the small model such that phi holds on A. So every formula of positive measure has a realization in the small model. Okay, so generalizing the corresponding notions for types. Okay, so the first result that we proved with Kyle Gannon is that in an IP group, both of these sets with respect to the convolution operation are compact and again left continuous semigroups. So left continuity here is less obvious than in the case of types, where it's just immediate from the definition. So here we actually have to use an IP in an essential manner in our argument. So it might be true in general for Borel definable measures, but it's not so clear. So this is actually left continuity for measures seems non-trivial in this case, but nevertheless it is true in an IP groups. Okay, all right. So we have these two very nice semigroups, convolution semigroups on Keisler measures. Now note that if I just have a definable group in a general structure, there is no non-discrete topology one can associate with it. So I'm trying to compare now the definable setting with the classical locally compact topological setting. A priori, there is no topology. Okay, yet we can consider the support of a Keisler measure. So the support of a Keisler measure mu is simply the collection of all types over the same set of parameters, so that every formula in such a type has positive measure with respect to mu. So to every measure, we can associate a closed non-empty subset, the support of mu. Okay. Now, as I mentioned earlier, in the case of locally compact topological groups, the support of an idempotent measure is a closed subgroup. This is no longer true for idempotent Keisler measures, even if theory comes equipped with some nice topologies. So for example, you're in a non-minimal structure or something like this. So we don't have already this part of the classical picture in any straightforward way. Nevertheless, we can say a few things, restricting at least to in some special cases. So adapting some results of Glicksberg, we can show that in an IP group, at least for a definable Keisler measure, which is idempotent, the support of this measure with respect to the convolution product on types, yeah. So this is a set of types, so a subgroup of types, is a compact left continuous semigroup with no closed two-sided ideals. So the moral is that when the measure is actually definable in an IP, the supports, its support is still nice. It's still it's not necessarily a group like in the topological situation, but it is at least a compact left continuous semigroup, and we can say some things about the structure of its ideals. Where, let me just remark here, by a two-sided ideal, we say that I, a subset of a semigroup, is a left ideal if we have that for any multiplying by any element of I by any element P in the semigroup, we still get an element of I. Okay, and an ideal is two-sided if it's both left and right ideal. So we have this observation. So now we try to find an analog of those results of Glicksberg and Cohen, etc., which classify the idempotent measures in a compact topological group as the Haar measures on the closed subgroups. So what would be an analog in on the model theory side? Well, instead of closed subgroups, we consider it's natural to consider type definable subgroups in the case of model theory. So what do we mean by this? Well, as before, assume that our theory expands a group and assume that H is a type definable subgroup of this group, by which we mean that the underlying set of H can be given by a small partial type. So small with respect to the saturation of the monster model. Okay, so in this case, when a group is type definable, suppose we have a measure, a Keisler measure, which is concentrated on H, by which we mean that if some type is in the support of the measure mu, then it implies the partial type defining this, this group H. So basically the measure of the group H is 1, yeah? And moreover, this measure is invariant under right translations on H. In this case, it follows that mu is idempotent. Okay, so any invariant measure on a type definable group, invariant I mean translation invariant measure on a type definable group is idempotent. Okay, so we have this natural source of idempotent measures, invariant measures on type definable subgroups. Now, by analogy with the classical case, we might hope that this is all idempotent measures are of this form. So they have to come from some type definable subgroup. We can confirm it in some cases. Oh, and just a remark. So if we have an invariant measure on a group, we say that such a group is definably amenable. So this is just a definable analog of the usual notion of amenability. Okay. All right. So we have, so this hope, this expectation is true in some cases where the theory of our group is tame in the model theoretically tame. Yeah. So for example, if T is stable, if we have a stable group, then the following are equivalent for a Keisler measure. Mu is idempotent, 1, and 2, mu is the unique translation invariant measure on its stabilizer. And the stabilizer is a type definable subgroup. Okay, so namely, the stabilizer of mu is the collection of all elements G in the group, so that G times mu is mu. So the measure is invariant with respect to translation by elements of the stabilizer. Okay, so we have this equivalence in the stable case. So here I list some natural examples of stable groups. Now, the way to do it is in model theory, we have this method to recover a group from a generic chunk of a group. So what we use here is Khrushchevsky's group chunk theorem, or more precisely, its generalization to partial types due to Nivelsky. Okay, to actually find the type definable group here. Now we have some further results in progress. So in particular, we have an analog of this theorem for generically stable measures in abelian NIP groups and for some other classes of measures. But let me stress that in general, the picture is not as nice as in the locally compact case for topological groups. So in the definable situation, already for an IP, already in the same setting, idempotent measures are not always connected. It seems they're not always connected to type definable group in any obvious way. So the general classification of idempotent measures seems to be a fascinating question, and it's open. But at least we have some partial results which demonstrate connection to type definable groups. Okay, so this is the first point, trying to understand what idempotent measures look like by connecting them to some definable or type definable algebraic objects, subgroups in this case. And the second natural direction is to try to understand the structure of the convolution semigroups. So to understand what the semigroups look like. Let me begin with some general theorem. It's a classical so-called Ellis theory, which provides some very useful information about ideals in left continuous compact semigroups. So here again, no model theory involved. Assume for now that X star is just an arbitrary left continuous compact semigroup. Then there exists a minimal left ideal I, and all minimal left ideals are automatically closed with respect to the topology on X. And we also have that we let ID of I to be the set of idempotents in this minimal ideal. So all U in I such that U square is equal to U. Okay. Then, first of all, there exists an idempotent in I. So ID I is non-empty. By the way, existence of minimal left ideal as well as the existence of idempotent in it. These are both things rely on Zorn's lemma. Now, two, for every idempotent in the minimal ideal I, we can consider the set U star I. So this is just the set of all elements of the form U star, let's say B, for B in I. Okay. And so the set is always going to be a subgroup of I with the identity element U, the idempotent. Okay. Moreover, the isomorphism type of this group U star I, it doesn't depend on the choice of I or U. Okay, so we have this canonical group associated to such a semigroup, and because it doesn't depend on all these choices we can make, we refer to this group just as an abstract group U star I as the ideal group of a given Ellis semigroup X star. Okay, so we call this the ideal group. Then we also have that the minimal ideal I is given by a disjoint union of subgroups of this form. So we have like U1 star I, U2 star I, etc. Yeah. So the ideal is just a disjoint union of groups of this form. Can I ask when do I have to stop, by the way?
Well, you have approximately 5 minutes.
5 minutes. Okay. Okay. Perfect. Perfect. So, all right. So now this is general theory. Okay. So this doesn't use anything about the particular convolution semigroups that we are considering. So let me then move to the next slide. Oh, can you hear me? It seems that I got stuck. The video got stuck.
Yes.
I do hear you.
But you can hear me still?
Yes.
Still,
Okay, okay,
Yeah.
okay. Because it looks like the video is stuck now. Okay, so I'll just continue then, as long as you can hear. So, okay, so now I want to say a few things about the structure of this convolution semigroups. So the first result applies to the convolution semigroup on types in an IP structures. So this was the so-called Alice group conjecture of Nevelsky with some modifications, refinement by Pillai, but it is also a theorem since some time ago that was proved by Pierre Simon and myself. So in a definably amenable an IP group, where we call definably amenable means that there exists a translation invariant Keisler measure. So in a definably amenable an IP group, we have that, okay, and let G be a small elementary substructure of G. So in this situation, the ideal group of the semigroup, convolution semigroup on the invariant types, on finitely satisfiable types, is isomorphic to a certain canonical quotient of our group, G mod G00, where G00 is the smallest type definable subgroup of G of bounded index. By bounded index, we mean that the index is smaller than the saturation of the monster model. Okay, where now I'm for some reason denoting this by the monster model. So this monster model of the theory of G. Okay, so in particular, the ideal group is often non-trivial in this setting. So this provides some connection between the ideal group and a certain canonical type definable object. So it's an internal object model theoretically. And such a subgroup also always exists, by the way. So the fact that G00 exists as a non-trivial theorem due to Shelach. And the situation is quite different, however, in the case of the convolution semigroups on measures, because of the presence of the convex structure, which provides us some further methods. So I want to summarize some results that we have about the structure of the convolution semigroups. So this is the last result. So assume that G is in an IP group, and let I be a minimal ideal of the convolution semigroup M dagger. So here recall that dagger means that can be either finitely satisfiable or invariant. So some of things I want to treat simultaneously. Okay. All right. So we have the following facts. So first of all, if we take I to be minimal left ideal, we have now that this is a convex subset of the space of measures. Okay, so recall again, we have the topological vector space structure on the set of all real valued measures, and the set of probability measures is a closed convex subset there. So it makes sense to talk about convexity structure. Yeah, and so the minimal ideal is convex. We also can see that it projects fully onto the Haar measure on this canonical quotient G mod G00. So namely for any mu, an element of the minimal left ideal, the push forward of mu is H, where H is the push forward with respect to pi, where pi is the quotient map from, oh, sorry, this should say G to G mod G00. The quotient map, and we can, since it leads to a continuous map from the space of types to the quotient, so it makes sense to talk about this push forward. And so they all project onto the Haar measure on the quotient, where this quotient, by the way, I didn't stress it, so it's a compact topological group in a certain natural way. Okay. So in particular, we can note that if the quotient is G mod G00 is non-trivial, then there are no types in I. So it only contains proper measures, not Dirac measures. Now, for any idempotent U in I, we have that the ideal group associated to this, so U star I, is trivial. Okay, so the ideal group is always trivial. In each of these cases, no assumption except for an IP on the group. And moreover, when we restrict to the minimal ideal, excuse me, the structure of the convolution multiplication becomes trivial. So we have mu times nu is equal to mu for any mu nu in I. So the convolution operation doesn't carry any information restricted to the minimal ideal. But in this case, what becomes informative is to understand the convex structure of the minimal ideal. So we want to understand it as a geometric object, because we see that convolution doesn't carry any algebraic information. And this is the second part of the theorem. But now we assume additionally that G is definably amenable, so has an invariant measure. And this is the last thing. So then, first of all, curiously, the picture becomes different in the case of finitely satisfiable measures and in the case of automorphism invariant measures. So for finitely satisfiable measures, all minimal left ideals are trivial. So every minimal left ideal consists of a single point, nu. For nu, a finitely satisfiable measure, which is invariant with respect to left translations, but by the small subgroup G. Yeah. So remember, G is an small elementary substructure of this curly G. Yeah. So we have this. All minimal left ideals are trivial. In the case of invariant measures, we actually know that there exists a unique minimal left ideal, which is also two-sided, in fact. And it's given precisely by those invariant measures, which are right translation invariant by the whole big group, curly G, by the monster model. Yeah. Okay. Moreover, the set of the extreme points of this ideal, so since it's a closed convex set, it makes sense to talk about the convex points, is closed. So in particular, this is a Bauer simplex. And we can have a description of this. So let me not go into the details of this, but for the experts maybe. We have certain descriptions. So all the extreme points actually given by certain liftings of the Haar measure on the canonical quotient with respect to certain generic types in this group, so-called F generic types. So this is an adaptation of some theorem of Pierre Simon and myself. Okay. And finally, in the case of FSG groups, so this is when we have not only it's definably amenable, but it also admits a translation invariant measure which is generically stable. We have that in both cases the minimal ideal is unique and trivial, both for invariant and finitely satisfiable. Okay. And the last remark is that outside of definably amenable, there are infinitely many extremal points. So, okay, so some moral is that I guess in the definably amenable case, we understand reasonably the structure of minimal ideals, but it seems that outside of definably amenable, that's a very interesting object to explore further. So we have some calculations and some examples, but in general, it's very open what happens there. Okay, so I'll stop here. Thank you very much for your attention.
Thank you very much for the interesting talk. Are there any questions or remarks?
Oh, hi, Artem. That's Krzysztof here.
Hi, Krzysztof.
Nice to see you. Yeah, so I just wanted to ask, because you have this convolution operation on this measure, so I guess it should be maybe the Ellis semi-group under the action of the convex whole of the group G or something like that.
Exactly. We show it. Yeah, I didn't discuss it, but yeah. So it's exactly.
But how does it go? Because okay, but there is also an option to look at the Ellis semi-group under the action just of the group G, and probably you will get another object then.
But
yes?
in an IP, you don't get anything new. You just this is the same as the Ellis group of the action on types in an IP.
If you act on measures, you get the same thing. You say the same Ellis semi-group.
But if you just act, yes, but if you just act by the group rather than its convex hull.
Yes.
This follows basically it's a result. I mean, it's a special case of some result of Glasner for time dynamical systems. And maybe to believe it, in fact, it might be in some form in your paper with Anand even also. Because no, if you just act by the group itself on measures are approximated by types very well. And so you can see that in fact, the Ellis semi-groups are isomorphic in the NIP case when you're acting by G on the space of types or by G on the space of measures. But to get the convolution of measures, you have to act by the convex hull on measures. And we show that then you get indeed the convolution measure on groups.
Okay, but if you do not assume NIP only Borel definability of measures, then it's not clear anymore that the Ellis semi-group for the action of G on the measures is the same as for the types.
Yeah. That's not clear. The main reason being we have no idea if convolution is left continuous outside of an IP. Like we don't even know if it makes sense if the convolution semi-group is even an abstract Ellis semi-group at all outside of an IP.
Okay, thanks.
But you're right. One can consider, I think, still the Ellis semi-group of this action, and yeah, it's probably a reasonable object to consider. But we focused on an IP.
Sorry, okay. So is it possible it is continuous? Sorry, I don't know.
So look, in recent time I became skeptical about that anything is true about measures outside of an IP. So maybe for Borel, if both are Borel, yeah. First of all, Borel definable. I mean, sorry. So the convolution product makes sense on Borel definable measures outside of an IP. So maybe, yeah. I mean, it wouldn't be crazy to expect it, but it seems there are counterexamples to all the basic properties outside of an IP now. So I don't know specifically for this, but yeah, it's unclear. We ended with, of course, we wanted to prove it without an IP first, but somehow the only way we could do it was using an IP in the end.
Okay, are there any further remarks or questions? If this is not the case, then thank you again for the nice talk.
Thank you very much. Thank you.
I close this session for today, but the breakout rooms will remain open. So if you want to continue your discussion, then you are welcome. So we will continue officially tomorrow. Goodbye.